Today we're going to look at one of the fundamental concepts of calculus. And that concept is the limit of a function. Now you really can't go any further in calculus until you have an idea about limits, until you at least have a preliminary intuitive idea about what's going on when we talk about the limit of a function. So that's what I want to do today. I want to help you develop the intuition about what we mean by limit, and then later we can look at a more rigorous mathematical approach to limits. But let's suppose we have a function here. Let's call this function f of x. And let's suppose that there's a point on that function, just above the 2 here. Now what we want to talk about is this. What happens if someone is on this function or something and they're coming from the left? What is their intended destination here? What is their intended height as their x value here gets closer and closer to 2? In other words, as they are just moving from the left to right. Likewise, if someone's moving from right to left, what is their intended destination? Now you can see it's the same. These two individuals would meet up, as is illustrated here. Coming along this curve, they both end up at the same location, which in this case it looks like it lines up to be 4. So we would say this. For this particular function, the limit as the x values get closer and closer to 2 from the left and right, the height, the intended height, is going to be 4. Now let's look at another example. Okay, once again we have a destination here and we're coming from the left and right. Now you notice I've got a closed circle here, so that indicates that the function exists there. Now that height I'm just going to call L. And you'll notice that what we have is this situation. What we would say is this. Since as we approach from the left, we end up at L, and as we approach from right, we end up at L, we say that the limit as x goes to a of f of x equals L. In other words, as the x values get closer and closer to a, in other words, as horizontally we get closer and closer to a from the left and right, vertically we get closer and closer to L. So notice, we've got two things. We've got what we call the left-hand limit. It says the limit as x goes to a from the left, that's what this notation is, of f of x equals L. And that deals with the left side of the graph. So that deals with that part. We've also got the limit as x goes to a from the right, indicated by this plus. It's kind of intuitive because it means you're coming from the positive side. That deals with the right-hand side. Now notice that both of those limits are the same. The left-hand limit's the same as the right-hand limit, so we say the limit exists. Now, in addition, in this problem, it turns out to be the same as if we were just evaluating the function, because you can note that if we plug in a into f of x, we get this. So there's no difference here between the limit and actually evaluating the function. So you might ask, well, why are we even talking about limits? Well, it won't always be that way. We won't always have the same values. Let's look at this one. Here we have approaching from the left and right, and now we have an open circle there indicating that the function does not exist there. However, even though the function doesn't exist, we still can see that as we approach from the left and as we approach from the right, our intended destination is L. We're still approaching the same height. However, f of a does not exist. So if you try to plug in a into that function, you wouldn't. A is not a part of the domain as is indicated by this hole. So this is an example where a limit would differ from the actual evaluating of the function, and you can begin to see why we would study limits. Because, the function is not defined at a, but it looks like it's defined every place else, near a. So we want to still be able to work with the function very near a, even if we can't actually plug in a. Okay, let's look at another one. So here we've got the same, a function looks very much like what we've been working with, except, now notice there's an actual jump here. As we approach from the right, we end up at a lower altitude than if we approach from the left. It looks like that the right-hand side will give you the limit as we approach A from the right, we get L1. And as we approach from the left, we get L2. Now, the left-hand limit and the right-hand limit exist. However, we say that f of x, or the limit as x goes to A, of f of x does not exist. That limit's not going to exist. Because the left-hand limit has to be the same as the right-hand limit. It wouldn't make sense to say, well, what height does the function get close to as you get closer and closer to A? Because you get closer and closer to two different heights. So as you approach from the left, you're intending to end up at L2. As you approach from the right, you're intending to end up at L1. So it makes no sense to say, where do you intend on ending up if you're on this function? Because the side matters. Okay, now let's look at an example of how we would use this information to evaluate limits. Let's start off looking at the limit of this function f of x as x goes to -6. Well, first of all, you look here and -6 is where an endpoint is on this graph. There is no left-hand limit. There's a right-hand limit, but no left-hand limit. So we would simply say that that limit does not exist. And the reason it doesn't exist is because for a limit to exist, it has to, from the left and right, it has to have the same end-up destination. And it doesn't there. It begins over here at the left. It doesn't have anything that's approaching. Okay? Let's look at something else. What about -5? Over here is -5. Now you can see that limit exists right away because obviously if you're coming from the left, you end up at the same level as if you're coming from the right. And that level would be 3. Now, the limit as x goes to 0, once again, you can just look at this and tell, okay, coming from the right, I end up at the same altitude as if I'm coming from the left. So that limit exists, and that limit would be 1. Notice that's, of course, the y value. Down here is the x value. Up here is the y. Now let's look at this one. As x goes to 3, this one clearly does not have a limit. It has a left-hand limit and a right-hand limit, but not an overall limit because there's a jump here. Notice, as we approach from the left, the limit is 3. See? As we're approaching from the left, we end up at 3. However, if we approach from the right, we end up at 6. Since that's the case, that would mean that the limit does not exist. We have a left-hand limit, a right-hand limit, but the limit overall does not exist.